eagerly waiting for that day when I can address all the students in person with in their physical presence. But had it been physical, possibly gathering all the 300 participants together at same place in the same auditorium would have been very difficult. So welcome all the participants. So as I said, that the topic that I have selected for this talk is on generative adversarial network. And I'll talk about the power of generative adversarial network, and I'll present the outcome of some of the research works which are done by research students in my group, and has been published in various international and national conferences, including International Conference on Image Processing, then CVPR, Computer Vision and Pattern Recognition, ICB GIP, and all that. But as I said, that I'll start from the basics. So quickly, within say 10-15 minutes, I'll touch upon the basics just to cover any person who is new to this field, so you don't be at loss when I go for this adversarial network. And again, as I said, that this will be on bird's eye view. Your detailed program, as has been told by Professor Oja, will consider each of the topics that I'm going to touch upon in this inaugural lecture. They'll be dealt with in details by the subsequent speakers. So to start with, what is meant by say machine learning? So I always start with these two figures, that can we recognize these two images? And I hope all of you can recognize that the image on the left is cave painting in Ajanta caves, and the image on the right is that of Parliament building in New Delhi. But that is not the question. The question is, how do we recognize, or how do we learn these figures? We learn these through various examples, which might have been shown to us by our parents, by our friends, or we might have seen such images in the textbooks that we have gone through during our school days. That is also fine. But the thing is, how do we remember that? How do I remember that this is actually cave painting and this is Parliament building? That is what is at the root of recognition, or that is what is at the root of machine learning techniques. So let us see that how do we go for such machine learning operations, or what are the things that you need when you go for machine learning. So when we talk about machine learning, we have a signal which is input to the system. Then, as I said that in the previous example, when I say that this is cave painting or this is Parliament building, definitely I have created some description of these two images, and those descriptions has been represented in some form unknowingly and stored in my brain. So whenever new images or new such objects are shown to us, we try to extract similar such description and associate that with the descriptions which are stored in our brain. And wherever we get maximum similarity or maximum match, we associate that unknown object with the object which has most similarity and is stored in our brain. That is what is machine learning output. And how you store it, that is what the learning is. So what we have at the input, we have input signal. The input signal may be visuals. The input signal even may be speech signals. So when we talk about machine learning algorithms, it has two stages basically. The first stage tries to find out some descriptors out of these input signals, and these descriptors actually represent the input signals that you have. And once you have these descriptors are given to the classifier. I can have different types of classifier like Bayesian classifier, support vector machine. We can have neural network classifier and different kinds of classifier like this. So these feature vectors are fed to the classifier, and if the classifier is trained properly with the domain knowledge of the feature vectors coming out from a particular domain, the classifier can classify this input signal belonging to a particular class. When I say it is a particular class, the class may be a class of dogs, class may be a class of birds, class of cars, and all those different things. When it is a speech signal, we can try to identify that who is the speaker or what has been spoken. So that is what is speech recognition or speaker recognition problem. Now, these are the domain knowledge that you have to extract in terms of descriptors or in terms of feature vectors. Now, it is this feature extraction that is what is domain dependent. Coming to the classifier is not domain dependent. Of course, the classifier has to know the different classes to which it is supposed to classify the input signals. But it is the same classifier that you use for speech recognition, the same classifier that you use for object recognition or image recognition. What is different is this feature extraction part. What kind of features we would extract from the input image, that is domain dependent. But the classifier knows only the features, and the classifier knows to which of the classes the features are to be classified. And that is what is the recognition. Now, come to this particular one. So what are the different types of features that we can extract? Suppose I have got these two different animals. You can always recognize that this is the shape of a horse, whereas this is the shape of a zebra. So the shapes are similar, but what makes a horse different from a zebra is the color and the texture that they have. Zebras usually have white and black stripes, which are not present in case of horses. So the descriptors can be two types of descriptors. One type of descriptor can be extracted from the boundary, that is shape, and the other kind of descriptor that has to be extracted from the information within the closed boundary. So those are the information like what is the intensity profile, what is color profile, what is the texture of that enclosed region, all that. So I can have two types of descriptors or two types of features which indicate shape, and also the features which gives you color, texture, intensity, all these different kind of information. I'll quickly go about that how these descriptors can be extracted. So how do you extract the boundary descriptor? So for example, we have this closed boundary. The simplest approach can be that this closed boundary can be represented or approximated by a polygonal shape. So given this closed boundary, I can have a polygon out of it, which roughly describes the closed boundary that you have or the shape of the boundary that you have. And once I have such a polygonal representation, I can have or I can measure what is the internal angle at each of the vertices of the polygonal representation. And once I have these internal angles, I can fit an autoregressive model, and the autoregression coefficients, they become descriptors of features. This is one kind of set of features or the descriptors that I can have. But while I do this, you remember my shape was this one, right? So there are a lot of detailed information, detailed variation in the shape, which is lost if I simply go for this polygonal representation followed by autoregression coefficients. But I can still code the detailed shape of the boundary. As you know that given this shape, when I go for polygonal representation, every edge of the polygon that actually segments the part of the boundary in a particular segment. So here I have shown this particular segment, which is shown over here. Now what I can do is, if I just rotate this segment so that the chord becomes horizontal. So this was the segment. The chord was at an angle theta with the horizontal. You rotate this entire segment by an angle theta. So the chord becomes horizontal. Once I have this, I can represent this as a function, right? So it can be, say, x versus gx, or gx versus x. And you normalize this so that the area under the curve is 1. This represents a distribution. And once I have distribution, I can compute different types of moments. So I can define second order moment, which gives you what is the spread of this particular shape. I can have third order moment, which gives you skewness, whether the shape is skewed towards left or the shape is skewed towards right. I can have fourth order moment, which is known as kurtosis. So all these different moments will be different for different shapes. And these moments can also be descriptors. So these are various kinds of shape descriptors that I can have. I can have various other kinds of descriptors, but I'm not going to all those details. My aim is just to give you an idea that what kind of descriptors or features that we can expect. Similarly, coming to the region one, we can have region descriptors, which is again, if I take the intensity histogram of this image, I get intensity distribution. You normalize this, it becomes the probability distribution of different intensity values. Similarly, if I have color image, I can have different color histograms, histogram of red component, histogram of green component, histogram of blue component, and all that. Okay, and of course, I'll have texture. So again, from these histograms, because if I normalize the histograms, this becomes a distribution. So once it is distribution, again, I can compute different types of statistical moments, as we have just said. And these statistical moments gives you the shape of the intensity histogram or the shape of the different color histograms. Those are also different types of descriptors. Texture is very, very important one. And it gives you a lot of information. Say, for example, if you go to the market, right, you get different types of oranges. Maybe it's the orange, which is produced in Nagpur, orange, which is produced in Darjeeling. They'll have similar colors, but the surface texture will be different. So I can distinguish between these two by texture analysis, though the color analysis may not give me the distinction. So there are different ways in which the texture information can be extracted, or the texture descriptors can be extracted. One of the way is if I want to extract the descriptors in the pixel domain or the image domain itself, then I can compute what is called co-occurrence matrix. The co-occurrence matrix, if I normalize this, it becomes joint probability distribution function. And once I have this joint probability distribution function, I can compute different types of features out of it. So for example, what is the maximum joint probability? I can compute something called element difference moment. Say for example, this one. Here you find, as it is I minus j, I and j are two different intensity values. So this element difference moment will be very low if most of the joint probability values are around the main diagonal of your co-occurrence matrix. Okay. Inverse to that, I can have inverse differential element difference moment. I can have uniformity measure out of it. I can also have entropy. So these are the different types of descriptors that I can compute from the texture in the intensity domain or the image domain itself. I can also perform the tasks or extract the descriptors or features in the transform domain. So for example, if you go for wavelet transformation, as you all know, that wavelet transformation divides your input signal into various subbands or frequency subbands. And depending upon the nature of the signal, the energy content of different subbands will be different. So this gives you the different subbands after doing wavelet decomposition of this image. Of course, this is a low resolution version. The high resolution version was 4 times of this. And these are the different subbands. If I have a different image, the subband contents will be different. Similarly, energy contents of different subbands will also be different. So if I simply compute the energy content of different subbands, they are also descriptors, and that I can differentiate between different types of textures that we have. One of the most successful technique for texture discrimination is what is known as Gabor filter. So here, this is what is your Gabor filter kernel. Gabor filter actually has three different parameters. One is frequency, the other one is scale, which is sigma, and the orientation, that is theta. So every instance of this triplet, that is orientation, scale, and frequency, gives you different Gabor kernel. And you convolve your image, given image with these different Gabor kernels, and the Gabor kernel output for different images will be different, right? And for each of these outputs, again, I can compute, in the simplest case, the energy content. And the energy content of different Gabor kernel outputs for different images will be different. That can also be used as descriptors. So all these different types of descriptors, if I put together or if I arrange in a particular order, what I get is a vector, and that vector is what is known as the feature vector. And all your classifiers that we have told earlier that uses these feature vectors to classify or to recognize the images. And these features are what are known as handcrafted features, right? But these handcrafted features have some problems. Let us see this Taj Mahal, right? So it is the image of a Taj Mahal, but are we sure that it is image of a Taj Mahal, an image of the Taj Mahal? Let us come to the next one. You'll find that earlier in the previous slide, what I've shown is this image, but actual Taj Mahal is this. So you find that from the beauty, Taj Mahal is much more beautiful than this, though structurally and even the color-wise, they are almost similar. So what kind of handcrafted features I can use to differentiate between Taj Mahal and this is what is Bibi Ka Maqbara? I don't know if you have visited this. Bibi Ka Maqbara is in Aurangabad, but as all of you know that Taj Mahal is in Agra, right? So I can't think of any handcrafted features which can differentiate between these two structures. So that is the problem with the handcrafted features or handcrafted descriptors. So can we automate this process? Of course, we can have a network which is known as Professor Oja mentioned, autoencoder. We can use autoencoders to extract the features. What is an autoencoder? Autoencoder is a neural network. Of course, like any other neural network, it has an input layer and an output layer. And in between input layer and output layer, I can have one or more hidden layers. So here I have shown an autoencoder architecture where we have just one hidden layer, and the number of nodes in the hidden layer is much less than the number of nodes in the input layer and the number of nodes in the output layer. Usually, the number of nodes in the input layer and the number of nodes in the output layer, they're same. So what you do with such autoencoder is that you feed your input image. At the output, I want the input image to be reconstructed back. So if my input image is X, output reconstructed image is X hat, I want to train this autoencoder in such a way that X and X hat are almost same, right? Initially, when the autoencoder is not properly trained, definitely my X hat, which is approximation of X, is likely to be widely different from X. And the difference in these two is the error. So I can compute what is the error between X and X hat. And you can train the autoencoder following the backpropagation learning algorithm or gradient descent procedure to find out what are the parameters or the interconnection weights which will minimize the error between X and X hat. Now, once the autoencoder is properly trained, I know given an input image, I get back output image X hat. And while doing so, the information flows through this hidden layer, which is known as bottleneck layer. And the number of nodes in this bottleneck layer is much less than the number of nodes in the input layer or the number of nodes in the output layer. So in the process, what this hidden layer is actually doing, because the information from hidden layer is taken by this output layer to reconstruct your images. So this hidden layer should keep sufficient information, but in a compact form, which the output layer or the decoder, this input part is known as encoder, the output part is known as decoder, that the decoder can use that compact information to reconstruct the image. So this compact representation I can use as my feature vector, right? So what I have in autoencoder is I have this encoder part, I have this decoder part. The encoder part encodes the image or gives me the feature vector or an intermediate representation. Later on, you'll see that we'll call this as latent vector. And the decoder uses this intermediate representation to reconstruct your original image. Now, the aim of autoencoder is not this reconstruction. What you are interested in is only this part. That is, I want that feature representation or compact representation of the input image. And this compact representation or the feature vector will be used for classification purpose. So what I can do is, here this is slide which shows that what does this autoencoder actually represent. So you find that these are the different blocks, which shows that given an input image, the autoencoder actually encodes, or the encoded output is nothing but different detailed information within the image. Yeah, so this is what I was saying, that in our traditional machine learning, given an input signal, we had a feature extraction stage, which was handcrafted feature. The handcrafted feature was given to the classifier for classification. We have automated this by using an autoencoder. And as I said, that autoencoder, though it has two components, encoder and decoder, but decoder is not of our interest. Our interest to use the decoder is only to train the encoder. Then you can forget about the decoder once the encoder is properly trained. And it is this encoder which gives you the feature vector. Now, this feature vector is actually decided or computed by the machine. I did not decide what kind of feature I want. It is the machine has decided that for a given kind of signal, what is the best feature, which is compact. At the same time, it has sufficient information so that you can get back your original signal. So your handcrafted feature extraction block is replaced by encoder block of the autoencoder, and then the other things still remains same. So this is what is traditional machine learning. When you go for today's deep learning, so yeah, this is another kind of representation that what these features vectors actually give. It is just an example, hypothetical example of the feature vectors or two-dimensional feature vectors. Suppose given an image, I can represent that image just by two components. And if I put that in this two-dimensional feature space, the feature vectors belonging to birds, they will form a cluster, something like this, because all those feature vectors are likely to be similar. The feature vectors corresponding to cars are going to form a cluster, something like this. Similarly, feature vectors corresponding to dogs are likely to form clusters like this. That means each of the feature vectors have a distribution, and the distribution depends upon the class of the object from which the features are computed. So that is what is class dependent distribution. Okay, and this is the kind of distribution that you can have, assuming that the distribution is Gaussian. And once you have this distribution, then your classifier can work on these distributions to classify these objects. Now, there are various challenges in this machine learning operations. Say, for example, I can have the images from various viewing angles. So this is the frontal view of Taj Mahal. This is the view from a particular angle. And you'll find that this view and this view, they are totally different. I can have images in different pose. I can have images under different illumination. I can have even intra-class variations. So these are the images of different chairs. So I can say that this is a chair, this is a chair, this is a chair, but we'll say that this is also a chair. So there is a lot of intra-class variation. You can also have challenges of distortion as well as occlusion. So your machine learning algorithms or the deep learning algorithms has to deal with all these different types of challenges. That means when you train your network, whether it is conventional machine learning or deep learning, the algorithm or the network must be trained with a large number of examples which covers all these challenging scenarios. Okay, so far we have talked about the conventional machine learning. Now what is the deep learning? In case of conventional machine learning, I had two different blocks. The first block was meant for feature extraction or the descriptor extraction. And then we had the classifier block, which works on these features of the descriptors to give you the classifier. Now you find that considering your machine learning, you are doing machine learning with a neural network. Typically, I'll have multiple layers of the neural network. And each layer of the neural network extracts information of a particular level of abstraction. So in case of deep learning, what is deep? If I go on increasing the layers in the neural network, as I said, that every layer extracts information of a particular level of abstraction. So the levels of abstraction in which the information can be obtained, that goes on increasing. And that is what is deep. By deep learning, you mean how deep your neural network is, or how many layers you have within, you have within the neural network. And once I have these deep neural network, then even the feature extraction part can be given to the network itself. So I can have a totally end-to-end machine where at the input I feed the image, and at the output I just decide to which class this image belongs, whether this image is image of a car or the image is the image of a dog. This network learns this whole thing from the given input signal to classification, right? And that is what is your deep neural network. So what you have over here, if you remember that Gabor filtered output, that slide we have, I had shown a Gabor kernel and an input image. The output image was basically the convolution output, where the input image was convolved with the Gabor kernel. So most of the features that we talk about, or which is used for classification or recognition purpose, those features can be extracted using convolution operation. And this convolution has to be done by different convolution kernels, and every kernel has a set of parameters, and those set of parameters can be trained, can be learned using your backpropagation algorithm. So this backpropagation algorithm will be covered in details in subsequent lectures. I'm not going into that. So right now, you just remember that the parameters of the network is trained using backpropagation algorithm, where the aim is just to tune the parameters so that your network is tuned for a particular application domain. So this is a generic architecture of a CNN network, where I have an input image, I have different convolution layers. After every convolution layer, I have a nonlinearity function, because usually the function that you map is nonlinear function. It is not always linear, and nonlinear function is very, very powerful. And what is this pooling mechanism? The pooling mechanism actually reduces the dimensionality of the vector or the feature map that you create over here. So it has two purposes. One is reduce the dimensionality so that your features are within a manageable size. And at the same time, the pooling gives you information to local to from local to global, right? At every location, at the at the input level, the information that you gather is very, very local, and the pooling helps to move the information from local to global domain. So this is a typical architecture, a generic architecture of a convolution neural network or a deep neural network. There are different architectures. This is again a convolution neural network, right? You'll find that towards the end of the convolution network, what we have, as I shown over here, it's a fully connected layer. This fully connected layer is nothing but multi-layer perceptron or multi-layer neural network, which are meant for classification or recognition. Whereas all these layers, starting from here to here, these are the layers which are meant for feature extraction. Okay, so up to here, the features you extract, which are given to the classifier, a multi-layer neural network usually, that gives you the classification output. So these are the examples of different types of deep neural network, which has been proposed by different authors, different researchers, and these are very, very famous. The one of the this thing is LeNet, which was used for handwritten character recognition. This is what is AlexNet. You'll get all these things in different books. This is a very famous one, which is actually GoogleNet, or also called Inception Network. Okay, and all these different architectures of the networks were the winners in ImageNet classification channels. Okay, so I just wanted to show you these different types of networks. Now, whatever I have talked so far, this is what is that kind of networks or the model. They are known as discriminative model. Why discriminative model? Because our aim so far was, given an input signal, I wanted to recognize or I wanted to classify that input signal, right? Or effectively what these models learn is mapping in the short that suppose I have an input X, which is sampled from a distribution Px, this network or this model actually gives me the probability of Py given X, where X is your observation and I want the output Y, where Y is the class. So given an input X, what is the probability that X has been sampled from class Y? Okay, that is, you discriminate among different classes. That is why this model is known as discriminative model. And how do you learn? Say, for example, I sample an X from a distribution of cats, and I have different classes, cat and dog. So my output probability can be that my input is cat, and I predict that it's a cat, in which case I don't have any error. But my input is cat, I predict it's a dog, then there is an error. So my learning is that using this error, you back propagate, and when you back propagate, you go on modifying or updating theta so that your model learns properly. It learns the proper distribution. And that is what is your discriminative model or discriminative learning. What I'm going to talk about today is not the discriminative one, but generative one. Richard Feynman said that what I cannot create, I do not understand. That means if I really understand something, I should be able to create that also, right? And that is what is generation. So if I say something is a dog, I should be able to draw a dog. That is what is generative model. So how do you train a generative model? You collect a large amount of data in some domains. So for example, I collect a large amount of images of birds, and I train a model so that the model can generate an image like a bird. Okay, that is what is expected out of generative model. So by this generative model, what I want is, as I said, that in case of feature vectors, what I have is I have different types of attributes, And from those attributes, you think of your auto encoder. The decoder part of the auto encoder actually takes these attributes of the descriptors, and using the descriptors, the decoder generates an image. So my generative model should be able to take such a descriptor and should be able to give me an image of corresponding to that descriptor. It is something like this. If I say that I have a feature vector or I have a set of descriptors which says that I have a big animal, the animal has 4 legs, it has big ears, it has a long trunk, it has pair of tusks, and so on, you can immediately think the animal that I'm talking about is an elephant. So I want that my generative model should be like this, that if I give the feature vectors, my generative model should be able to give me the image of an elephant. Then the question is that I have an autoencoder which can do the same thing. Then what is so great about the generative model? Of course, there is some problem with the autoencoder. The problem with the autoencoder is that autoencoder, the encoder part maps your input image or input signal to the feature space. But the feature space that is generated, it's a sparse feature space. That means the feature vectors that you generate, I'll just keep this because of shortage of time. Okay. So these are the 2-dimensional features created out of handwritten numerals from MNIST database. Okay. And you see that these are the feature vectors for different numbers. So these are the feature vectors corresponding to this numeral 7. And the feature vectors that has been created over this space, you find that this space is very sparse. When you talk about autoencoder, suppose I give to the autoencoder a feature vector which is somewhere over here. And this feature vector was never created by an autoencoder, but because this example, the autoencoder has never seen. So the decoder, because it has not seen this feature vector, will not be able to generate your image properly. It can give you something garbage. Okay. So as I said, that the purpose of autoencoder is to train the encoder so that it can give you the feature vectors, and these feature vectors are sufficient for classification purpose, for recognition purpose. But this feature space is not enough for generative purpose. Because for generative purpose, I want a continuous feature space. Or in other words, I want to learn a distribution. That is, given a class of images, say for example, large number of images of bird, I want a distribution of the feature vectors of the features extracted out of those bird images. So that if I just sample a feature vector from that distribution and feed it to my generator or the decoder knows that this has come from the distribution of the feature vectors corresponding to bird. So what it has to reproduce is a bird image. That is what is expected of a generator model. And of course, we can have a generator model. I'll just skip this. So here what we want is, so these are the features which are extracted actually by an autoencoder. Say, there's a particular feature, say smile. This fellow, you find that he's not smiling at all. This boy is not smiling at all. So this smile attribute has a negative value. Here it is almost neutral. So it has a value 0. This kid is smiling a lot. So this smile attribute has a positive value. This is what is given by your autoencoder. But for generation purpose, we don't want such a discrete values, but we want a probability distribution. A mean position, which indicates that where that attribute value should be placed, and a variance or a standard deviation telling you that how much is the variation of that particular attribute value. And this kind of encoder of the generator is what is a variational autoencoder model. So a variational autoencoder model can be put like this. So this is a variational autoencoder model. You find that in case of autoencoder, here we had the feature vector, but a variational autoencoder actually learns a distribution, mean and variance. It does not give you a discrete feature vector. So once this is learned, the variation autoencoder learns this distribution. Then from this distribution, you can sample a feature vector, which is given to the decoder, and the decoder will generate the image. Okay. So this is one model of generation, or one of the generative models. And using such autoencoders, you find that these are all synthetic images, which has been generated by this autoencoder, and they're quite close to natural images. This autoencoder also follows this algebraic relation. So suppose I can have the latent code of the feature vector computed from faces with glass. I can also compute the feature vectors or the latent vectors using faces without glass, and the difference of these two gives you the latent vector corresponding to glass. So what is the advantage? This gives you an example. Here I have a number of faces with glass. Here I have a number of faces without glass. You get vector from this, the latent vector from this, latent vector from this. Subtract these two, you get the latent vector of glass. Add that to the latent vector of another face without glass, and you can generate the faces with glasses. Okay. So these are the things that you can have using variation autoencoder. The other kind of generative model we can have is what is known as generative adversarial network. So here the concept is that I have two networks. One is the generative network, and the other one is adversary or critic. So the generative network takes in a feature vector or the latent vector, and from that latent vector, the generative network generates an image. And the adversarial network or the critic uses this image and tries to tell the generative network that what you have generated is fake, it is not an original, or it is not a natural. And that error is fed back to the generative network for tuning its parameters or updation of the parameters. So I have two training involved over here. One is the adversarial network must be trained so that it can distinguish between natural images and synthetic images, which are generated by the generator. And the other training is for the generative network, that by taking the feedback from the adversary or the critic, it can fine-tune its parameters so that the generation becomes more and more fine, closer to the natural one. So when you do that, so basically what does this generative network does is, suppose this is the true distribution of the data, and the generator network produces another distribution, something like this. So as the training goes on, this distribution of the generated data is mapped to the distribution of the real life data or the natural data. Okay, so this is what your adversarial generative network does. And for training this adversarial generative network, as I said, that I have two steps of training. This is what is your generator, this is what is your discriminator. Both of them are neural networks, and they have parameters. So for training this, I had to define what is the loss function. So for the training of the discriminator, the loss function is this. You'll find that this is the log likelihood value. This is the discriminator. It gets an input X, which is the real one. It also gets an input from the generator. The generator is G. Z is your input latent vector. So using this input latent vector, the generator G produces an image. Okay. So when you train the discriminator will try to maximize this probability, and the discriminator will try to minimize this D of GZ. Okay, or it tries to approximate maximize this. So this maximization of this objective function is to be done when you train your discriminator. Similarly, the other part is training the generator. So during training of the generator, you try to maximize this. Okay, so the maximize d of gz, or overall you minimize log of 1 minus d of gz. So you find that when you tried to train the discriminator, you had maximized this. When you train the generator, you have to minimize this. Okay, so that is how the discriminator and the generator, they are to be trained one after another, so that the generator becomes very strong to produce images which are almost real, and the discriminator also becomes strong so that it can discriminate between the real image and the fake image or the generated. So using this, these are the outputs which are produced from such generative adversarial networks. So this was a paper published in ICLR 2018. Similarly, for using this generative adversarial network, you can do this sort of image translation operation, right? So given this, your semantically segmented image, you can generate a real looking image. Given a black and white image, you can generate color image. Given sketch, you can actually generate an image out of it. So all these are possible using this generative adversarial network. You can also use this for super resolution of the image. So this was a paper which was published in CDPR 2016. You can also go for video to video translation, as shown over here. This is something what is known as TileGAN, which was published in 2018 again. How much time I have? Yeah, I still have some time. So now let me produce that how we have used this generative adversarial network for a very, very important work in image processing, which is known as semantic painting. So semantic painting is something like this, that suppose I have an image where part of the image is corrupt, right? During training, we'll call this as masked image. So purpose of semantic painting is that you try to cover this portion such that you get a real looking image. The remaining portion of this image will be same as the masked image. And within the masked region, you generate part of the image which is consistent with the visible part of the image, right? So this is what is in-painting operation. And this can be done by this generative network, where what we do is you synthetically generate an image in such a way that will be similar to this with this masked portion filled up. Okay, so it is not that you are just covering this part, it's a new image that is being generated. And how you do it? I'll just skip this portion. Yeah. So the usually what is done is that suppose I have this image and I also have an image or pair of images where one image is complete and the other image is partially masked. And the network, this when passed to the network generates your full image and you try to find out what is the error between the masked image and the corresponding portion in the unmasked image, because I have the ground truth. But in case of generative one, we are not doing that. We don't have that ground truth anymore. So we don't have any explicit reconstruction loss because I don't have information of what is there in the masked image. So the losses that will be imposed is only from the visible pixel, which is known. And that is why they are all unsupervised losses. So it is something like this. You sample a latent vector from the latent space, pass it to the generator. The generator generates an output image. From this output image, you try to formulate a loss function where loss function will consist of two components. One component is the loss which is given by the discriminator or the adversary, saying whether it is natural or not. And the other one is the loss function, which will be computed over the visible portion or the portion over which the information is available. Using these two loss components, you try to iterate on your Z vector or on the latent space. That means you are searching for a better latent vector, which will give you a perfect image. So this is what shows you that particular path. You start from an initial one, then come to a final one. Okay, where this final one will be natural looking. At the same time, all the unmasked portion of this and unmasked portion of this final image will be almost similar. So this is what is your in-painting network. So the kind of loss that I have is, one is perceptual loss, which is given by the discriminator. As we said, the discriminator will try to minimize this, or the discriminator will try to maximize this component in D of GZ. We have this contextual loss, which is computed out of only the non-masked portion, right? So Y is your input image. This is the unmasked portion of the input image, and this is the unmasked portion of the generated image. You'll find out what is the difference between these two. So that is what is contextual loss. And that total, this contextual loss, as I said, will be computed from this unmasked portion and the unmasked portion of the synthetically generated image. And finally, the loss function that we have to minimize is the total loss function, which is given by this, right? And now what you are doing is you are actually iterating on the Z vector, not the parameters, because your discriminator and the generator, they're already trained. So I have an iterative approach to find out what is the proper Z vector, which can give me a proper deconstructed image. But it's still an iterative process. This visually tells you the same operation that I have just said. It's an iterative process. Because it is iterative, it is time consuming. So we have, this visual just tells you, just gives you a feeling of how iteratively the image is getting refined, starting from an initial one. So this is the masked one, then the first one, then over the time, over the iteration, the image is refined. Okay. Now what we have tried to solve is that can we have a smarter initial solution? Because the number of iterations that you need to converge to a proper latent vector, that depends upon what is your initial estimate. So we have tried to solve this or try to reduce the number of iterations by having a better initial estimation. And this work was published in International Conference on Image Processing in 2019. So what you do is, this visual simply shows that using a random initialization, as is done in the previous work by A, given this masked image, the initial estimation is something like this. Okay. Similarly, over here, the initial estimation is something like this. And we want to have a better initial estimation. So how we can do that? One of the possibilities is, and that is what we have tried, is that you can have a pool of feature vectors which are pre-sampled, and for each of the pre-sampled feature vector or the latent vector, you have the generated image. Now, given a masked image, you take that particular generated image which is nearest to it. Okay, so it is something like this. These are the pooled generated images. There's the masked image that is given. Out of this pool, you select that particular one and the corresponding Z, which is nearest to it. Okay, that means when you compute the nearest one, you have to have a similarity between this, and the similarity is computed over this unmasked portion only. And that is what is your initial Z value. And because your initial Z value is nearer to the actual Z value, as we have computed from here, the number of iterations that you need to converge to proper Z value is likely to be very, very low. And that is what we actually got. So this is the one which we have, that this is the masked image, okay? And when we go for this nearest neighbor search, using the nearest neighbor search, we get an estimation, something like this. And when you go for this similarity, the similarity is based on the intensity values in the unmasked region, which is given by this. And also, we go for structural similarity, that is, take the gradient of the unmasked portion of the generated image and the corresponding input image. And the gradient difference is also part of the loss. So this ensures that your initial estimate will have similar pose, similar details, and the similar size. Okay, so some of these two, based on some of these two, you go for your initial estimate. And if we do that, you'll find that it says that, suppose this is the masked image that you have, a random selection of Z value gives you this initial estimate, and using the proposed technique of selecting the nearest one from a pool of images gives you this initial estimate. So you find that this actual masked one or the distorted one and the initial estimate, they are very close. Similar for these two examples as well. And because your initial estimate is very, very close, the number of iterations that you need will also be very, very, very small. Say, for the earlier one, which I presented, average number of iterations is 800, whereas in our proposed case, the average number of iterations is around 30. And this is the result. This is the masked image. For ES paper, this was the output, and for our proposed one, this is the output, because we have considered not only the pixel difference, but also the gradient difference. Okay, that is why your output has been better. Similarly for other two examples also. Then we have extended this technique for video in painting, because in case of video in painting, if you have corrupt video, nearby frames are very similar to each other. So what I can do is, I have an initial Z vector for say frame t minus 1, and with this Z vector, I reconstruct frame t minus 1, and while reconstruction, I come to through iteration, I come to a Z vector, which is zt minus 1 final. And as I said, that because nearby frames will be similar to each other, so this zt minus 1 final, that is this one, can be taken as initial estimate of the feature vector for reconstruction of the tth frame, and so on. And in addition to this, the other kind of constraint or the loss that you can put in place is what is known as group consistency loss. Because if I consider a group of frames which are temporally close, then the Z vectors or the feature vectors, the latent vectors corresponding to each of those frames are also likely to be very close. So you compute the mod of the difference of consecutive Z vectors and sum of those differences over this neighborhood or over this window of frames. This should be minimum, okay? And by combining these two, you can have the overall loss function, by minimizing which you can go for video in painting as well. So this shows the output. So these are the masked video frames. This is the video frames which is generated by Ye et al. And this is the set of video frames which is generated by our proposed technique. And here the advantage is we have gained almost 800 times in terms of computation of the number of iterations. Then we thought that still we have an iterative process. That means we are refining the Z vector iteratively. Can we avoid this iteration altogether? So this is a paper which was published in CPPR 2020, where we thought that let us train another network which can predict the correct Z vector given a corrupted image or a corrupted frame. So that is what we are calling as prior guided single pass GAN based in painting. So the idea is something like this. I have, this is our GAN or generative adversarial network that gives you the correct image or the repaired image given distorted image at the input. And up to here, selection of the proper Z vector was iterative. Now this work extends further that it has another prediction network. The prediction network tries to predict what should be the Z vector that should be fed to the generator for generation of the image given your distorted image ID at the input. Okay. So here the thing is something like this. In order to train this predictor network, again, I have to have different types of loss, which is to be minimized. One loss is, of course, we are calling it as perceptual loss or photorealism loss, which is given by the discriminator over here. So this is the discriminator, which gives you perceptual loss or the photorealistic loss, realism loss. Then we have defined another loss, which is called spatially adaptive contextual loss. So what does this spatially adaptive contextual loss does? Given a corrupt image, so think of an image like this, yes, over here. So this is my masked portion. What I want is that when this masked portion is filled, then there should not be any disrupt change of intensity or texture from this unmasked portion to the masked portion. And in order to do that, the error value that you compute, that should have more weightage to this mask boundary than at other points. So that is what is our next component of loss, which is given as spatially adaptive contextual loss. Okay, and that can be computed over here by an weighting function. And the other one is, we have used that before also, that is gradient difference loss, which is take the gradient of the difference of your input distorted image and the generated image, and this gradient both in x direction and y direction. So this ensures that the image that will be generated, that will not be blurred, but it will be rich in high frequency content, or it will have the detailed information, and also all the structures will be retained, its orientation will be retained. And the total loss that you minimize for training of the prediction network is weighted sum of all of them. So this is the total loss that has to be minimized for training of your prediction network. So it's a two-step training. In the first step, you train this generative adversarial network, as you have done before. And in the second step, you train this prediction network. And when both of them are trained together, I have an end-to-end network, which gives you an output image in single pass. So you feed your corrupted image or the degraded image at the input of the predictor. The predictor predicts the Z vector or the latent vector. The latent vector is given to the generator, and the generator gives you the generated output. Finally, your reconstructed output is the degraded image plus the masked portion of the generated image. Because the generated image was full, you take the masked portion of it, feed it into this degraded image, and that gives you the reconstructed image, which will be complete. Okay. Now, there is another problem. The problem is the generator network output can be multimodal. How can it be multimodal? Let us take an example. The example is, suppose this is my actual image, and this is the masked image of the displayed image. It is possible that the generator will generate this output, the generator will generate this output, the generator will generate this output, the generator will generate this output. You find that all these outputs are equally probable. Okay. Now, this is fine as long as a static image is concept, because the images are photorealistic, okay, and they're quite fine. But if I use the same algorithm for video in painting, then you think what will happen if the first frame which is generated is this, the second frame that is generated is this, the third frame which is generated is this, the fourth frame which is generated is this, the fifth frame that is generated is this, and so on. You find that the output frames, when you play in the form of a video, that video will be very, very jittery, right? So we have to ensure that the frames which are being generated by the generated network, they are consistent. So for doing that, what you can use is what is known as a condition gap. So what is important is that if you have a smiling face, the smile is reflected not only in your mouth or the lips or the teeth. The smile is also reflected the way the eyebrows are bent, the way you have wrinkles on your face. That means the overall structure of the facial image will be different for different types of emotion. If it is smiley, overall structure will be something. If the fellow is angry, the overall structure will be something else. So can we precondition the image that has to be generated by the generator with such structural information? Okay. So if we condition that with the help of structural information, feed your generator or train your generator, train your discriminator, train your predictor using such preconditions, then you find that all these are probable, but there is a decreasing order of probability. That means which is the most probable image that I can estimate. So how do you put such a condition? For a face image, there are a number of landmarks, which was proposed in ICCV, International Conference on Computer Vision, in 2017. There are a number of landmark points in a face image. Okay. But the problem of using this is that in the masked region, the landmark points cannot be estimated correctly, right? So you can assume that these landmark points that you are getting in the masked region, they are the noisy points. And this noise is to be filtered out. So for doing this filtering operation, we have used an autoencoder, which is known as denoising autoencoder. So the denoising autoencoder can take this noisy input and give you the filtered output. Okay. So using this, you can have that structural information, and using this structural information, you can train this generative adversarial network, and this generative adversarial network will give you an output which are consistent outputs. Okay, so you feed both of them, your set of landmarks, which gives you the structure, and also the degraded image or the masked image, and you get the proper output from your regenerative network. So here some examples. Say, for example, here I have the same Z vector, but you have different set of landmark points from the facial image. And with this landmark points, you'll find that though the Z vector is same, but you have different generated image. And same is over here, and this is what is known as structural prior, and accordingly the GAN we have named as prior guided generative adversarial. Yeah, I'll just give you an example of or another work which was published in WSCV 2019, again using generative adversarial network, but the aim of this generative adversarial network was quite different. It was domain adaptation problem. Now, what is this domain adaptation problem and how is it important? Say, for example, we have well-established object detectors. So, for example, Professor Oja was mentioning about RCMN network. The network is trained for detecting objects given within static images. So, for that, we have, say, Pascal VOC database, where we have large number of annotated images where what object is present within the image that is specified, those are annotated. But we don't have any such database for video objects, okay? And annotation is very, very laborious problem. So the aim is, as we have large annotated database for static images, can we go for domain adaptation? That is, same annotation, can it be used for training networks meant for detecting moving objects? Now, why this moving object detection is so challenging? The reason being that whenever I have moving objects, the moving objects or the images containing moving objects, they suffer from a kind of degradation, which are motion degradation or motion degraded. That means your image will be blurry. It will have a drawing effect. The intensity value of the texture will not be that sharp. The image is usually low resolution, unlike the high resolution images that you have in Pascal VSC database. So if we can adapt this knowledge from the static image database to moving object database without going for any manual annotation of moving objects, then training of the networks for moving object detection will be very, very simplified. So it is a very, very important problem. And this problem, so these are a few examples. Say, for example, when you have static images, you find that the static images are all very high quality images. They are very sharp. The resolution is very high. Whereas if you have moving images, so these are the quality of the moving images. You find that the images are usually starred, usually blurred. The color information, that is also blurred, okay? Intensity is very, very disturbed. The texture is disturbed and all that. So a network which is trained on static images, if I apply that onto this, the network will usually fail, okay? So that is where the importance of the problem is. And the way we try to solve is, as we said, is the domain adaptation. This is what is a domain adaptation example. Considering this as the domain of horses, this as the domain of the zebras, you can adapt the knowledge that you get from horses to the domain of zebras. So you find that just the body texture has been changed, okay? So this is what is domain adaptation problem. So what we want is, so we have a large number of static images, say from Pascal VOC database, and you, through a generative network, these images you converge to video frame-like images. Okay. So for doing that, I have to have a generative network, which will generate a video frame, and then I have to have an adversary. The adversary will tell you that whether this generated video frame is similar to real video frames or they are very, very dissimilar to real video frames, or they are fake video frames. So using that, your generator network will be trained. I also need a reverse process. Why reverse process? Because I have to ensure that, suppose I have image of a dog, right? Your adversary takes large number of video frames per video frames just gives you what is the characteristics of the video frame. It does not have any knowledge of whether that video frame contains a dog, it contains a car, it contains a plane, and all that, right? It simply says what is the characteristics of the image that has been created and whether these characteristics matches with the characteristics of the examples that you have from video games. So it may so happen that I have a dog, a static dog. I'm translating that to a moving dog. And while doing that, the frame that you have generated is not of a dog at all. It might be a moving car. Or maybe the size of the dog has changed, its orientation has changed, right? And the frames that you generate in such a way may be useless. So to ensure that, you also have a reverse path. So what you implement over here is a cyclic GAN. That is, whatever you regenerate, I have to have a forward transformation. Similarly, given a video frame, I want to reconstruct a static frame corresponding to that in the reverse path. In addition, I also have to implement a loss. So these are your GAN losses for the forward path and the reverse path, using which your generative adversarial network forward and reverse that will be trained. You also have a data loss in the sense that I make sure that this X, suppose this X was a cat, okay? Using this X, I transform through this function to this generator to a moving one, okay? And then this has to be retransformed into original X, okay? So you find out whether this retransformed X and your original X that you have, what is the loss between these two, what is the error between these two. Similarly, in the backward one, I had a moving object Y. Using Fy, you have transformed to a static object. Again, using G, you have transformed back to the moving object. So this retransformed moving object, the moving frame, and the original Y moving frame, how much is the difference between these two? So all these losses have to be minimized. So the total loss that you have to minimize is given by this expression. These two are the generative adversarial network losses, forward and reverse, and these two are the reconstruction losses or the data losses in the forward path and the reverse path. All these losses have to be minimized together to train your cycle GAN, and once it is trained properly, then given a static input image, I can generate the corresponding video frame. Now, for training your network for moving object detection, these generated video frames can be used, but the annotations remains same as your annotations of the static images. The annotations does not change, right? So I have large number of annotated video frames, but these video frames have been generated from the static frames or static images. Coming to the performance, come over here. Yeah, this is the one. So this was a video frame where the object detector like FRCNN was used, and you find that FRCNN could detect only this man. It failed to detect this dog. Whereas with our proposed one, we have been able to detect both the man and the dog. Similarly, using FRCNN, this is another video frame, you find that it has been able to detect this car and this car because they are very sharp, but it has failed to detect this car, which has motion blur. But using our proposed technique, we have been able to detect all of them. So in the same manner over all these different images. So you find that this generative adversarial network that is useful in various domains. I have slides on other domain as well. It can be used for in the medical imaging domain. We have also used this generative adversarial network for denoising of a low-dose CT image. What is low-dose CT image? When you go for multiple CT scans, every CT scan subjects you to large amount of X-ray radiation. So if you go for a CT scan with low radiation, that is what is low-dose CT scan. But in such cases, the scans that you get, they will be noisy because the energy, the X-ray energy that is being injected, that is very, very low. And such CT images may not be suitable for diagnostic operation. So what you have to do is, given those low-dose CT scans, you have to reconstruct something like normal dose CT scans so that all those noises or the artifacts that are generated present in the low-dose CT scan image is removed. And you can improve upon the diagnostic quality of the low-dose CT scan images. We have used this GAN network for that problem as well, which is taken as a problem or the image translation problem from low-dose CT scan to normal dose CT scan images. We have also used this GAN network for document image processing. So this earlier one was published in IEEE Transactions on Medical Imaging just a few months ago. We have also used this GAN network in document image processing. So one of the problems in document image processing is now we are all going for a digital world, but we have many manuscripts which are handwritten, particularly legends like Rabindranath Tagore, Satyajit Ray, all of them. So when you have those handwritten manuscripts, usually the handwritten manuscripts along with the letters, they also have sketches. There are strikeouts, words. Suppose by mistake you write something and you want to strike it off. So there are strikeout words. There are few words or few sentences which you feel to be very important. You go for underlining. When you go for strike off, different people have different style. There may be cross, there may be single line, there may be multiple lines and all that. And these such kind of handwritten documents, if you feed to an OCR, the OCR does not perform well. So what you have to go for is filtering of such kind of strike of words, underlines, and all those different things. So we have also used this GAN network for such filtering operation or for removal operations, removal of the strike offs, removal of the underlines, so that the text, handwritten text that you have, that becomes clean and it can be used for digitization purpose. And this is the work which was presented in last ICVGIP Indian Conference on Computer Vision Graphics and Image Processing. So you find that this generative network, whether you use generative adversarial network or whether you use VAE or variational autoencoder, they are very, very powerful and can be used for various tasks related to computer vision and graphics. Okay. So I hope within this short time, I've been able to give you an idea of what computer vision tasks is, what is machine learning, what is deep learning, and the power of generative deep learning, generative network, and how these generative neural networks can be used for various computer vision as well as computer graphics tasks. I think I'll stop here. If there is any question, I'll be happy to answer that. Thank you.
Thank you, Professor, for such